later on. I think we are going to have we're going to cover an exciting part of our calculus journey tonight. And, just to recap a couple of sentences or maybe a couple of paragraphs about it is that we looked at the geometric interpretations, if you perhaps remember what Cavalieri did, with constructing a square on top of a parabola, and then, somehow he found that the volume of the generated squares is 1/3 of the cube. So we came to know that, the area under the curve is 1/3 of x cubed, and we know y equal to x squared is the curve. So, several such things. So we Apurva dealt with secant becoming the tangent, and the slope of the tangent is rise upon run. And we came to know that, this algebraic sort of playground got a perfect setting in geometric interpretations. We can do this with periodic functions like sine and cosine. If you guys are aware of how the sine and cosine are actually projections of the unit circle in x-axis, and that has got it's a beauty of its own. So we looked at some of these geometric interpretations. We also understood the fundamental theorem of calculus. I think, like I have been always saying, if you forget everything else, and if there is only one thing that you could remember or take back from the series of discussions that we had or have been having, then that is this really the fundamental theorem of calculus. There is a reason why it is fundamental, and we'll cover the part of the reason tonight. We peeked at calculus through history, of course. There is a lot to learn from history, and I urge you to look at what our ancestors did in any particular field of endeavor. History as a subject, when we learn that in school, then it is mostly revolving around sociology or how societies behave and politics and governance and things like that. But everything has a history, right? History is like you can have the history of mathematics, history of physics, history of chemistry, and basically history of everything. One good thing about history, in my personal opinion, and we can discuss this, is that we can basically shrink the time when we are looking at what our ancestors did. People have spent lifetimes on one single problem or one single small narrow area, but we don't have to do that. We can sit here and take a good overview of what they did over their lifetime of, let's say, 20, 30, 40 years in a matter of few days. That's a huge advantage, right? We can keep things in perspective, but we can also shrink the time. So we looked at some of that, right? We looked at how Newton came through his insightful observation, and how Leibniz did some of the things that he did, and all the other mathematicians, right? There was a strong correlation in between all the things that they did. Valuable insights are bound to spring from such exploration that they did, and that's what happened. Calculus is slightly conceptually, the first thing that we learn in the realm of higher mathematics, right? We have arithmetic, we have algebra, we have geometry, and then we have this thing called higher mathematics. and it starts with calculus. So we did some rudimentary proofs of these things, right? But we did not do many rigorous proofs. Obviously, Apurva did deal with some of the things somewhat rigorously. But this kind of thing, when you learn, now you'll enter your college, and then beyond that, you will learn all the underpinnings of calculus in a course that's called analysis. Analysis of real variables, analysis of complex variables, analysis of vectors. These are really very, very involved areas. And there you have rigorous proofs of various theorems. But we did get a taste of it. We did not say that FTC just falls from the sky and we are there. We tried to prove, we found that the area under the curve can be said to be what we started with, right? In the proof of FTC, the rudimentary proof. Today we are going to spend some time on notation. Like I said 2 weeks ago, what happens is, we'll come to know about notation, and then, if we have time, perhaps in the last lecture or last discussion session, we will look at applications. And so we will start with that notation. Now, an inseparable part of any language is, of course, its symbols, right? We start learning languages from a young age, and we come to know about symbols, right? And beauty of language is that the set of symbols is finite. It can be small, or it can be short, or it can be long. Like in case of kanji character, there are many characters, right? In case of Devanagari, there are about 46. In the case of English or Roman, 26. And then there are numbers, right? And so they're still finite, they're not infinite. But what gets created is infinite. The language itself is infinite, right? We can create strings of those characters which are not repeatable. So we can create infinite things. So languages are by definition infinite. Now Leibniz is credited with creating the symbols or the notation of calculus that we are in use, that is in use today, right? If we don't understand this notation, then we might have some issues, right? So I think it's important, it pays to pay attention to the notation, right? Notation also shows some part of the history and also evolution of concepts, right? I'm sure. So, I know that, some of you have dealt with calculus concepts in textbooks, and you might not have heard the word quadrature being used, right? Quadrature, we came to know that it is the area under the curve. And most of the textbooks will deal with area under the curve, but its name was quadrature. So, all this evolution is part of the notation that is there in the use today. So we want to speak the modern language, right? We don't want to live in the past. See, the point is that when we want to learn from history, we don't want to dwell in history. We want to live in the present times, right? So we need to learn the notation that is in current use. So we learn from the history, but we become very, very, very familiar and conversant with the present day notation, right? So what we'll do is that we will restate the fundamental theorem of calculus in the form of new notation. And Apurva has used some of the notation, like, delta x and dx, like when he was showing the math animation that he did, that delta x becomes dx. And so we have used some of it, but we'll get into the details of it. All right, so let's see. So, this is a general curve. We have been dealing with this kind of curves all through this set of discussions, right? So what Leibniz did in 17th century is that he viewed the distances between these marks, like you can see that the marks are A and D, C and F on X and Y axes. And what he did was that he chose the notation, just the letter D, just the letter lowercase English or Roman D to show the difference, right? And following that, he just placed the variable like dx is nothing but the difference in x. dy is the difference in y. Not the actual value of the variable, but the change or the difference in that, right? He just said that this seems very straightforward. And so in this case, what will happen is AD is the distance on the x-axis, the difference between A and D. So we show it as dx. Similarly, FC is the distance. See, the point is that F and C are the reflections of these points on the curve, right? It's not like F and C are some random points. They are the reflection of this curve on the y-axis. And since there is a difference between them along the y-axis, we denote it as dy, right? So clearly the slope of this particular hypotenuse, we're still not drawing tangents. We're just drawing the hypotenuse like BE in this case, right? B and E are not really on the curve, but they are, maybe we should say that they are on the curve, but the BE segment is not the part of the curve. We are just joining it directly, right? So when we join this directly, BE becomes the hypotenuse, and the slope of that hypotenuse is obviously FC upon AD, and he called it dy by dx. Now the problem is, unless we go into, like we said, analysis, these things will not be completely clear to you. But you guys are still too young, so we don't want to inundate you with all the details. And for now, you can just reconcile with this the way Leibniz did. Leibniz said that dy is extremely small, dx is extremely small. So the ratio of these really small entities is what I'm interested in. And I'm just going to call it dy by dx. So in other words, dy by dx is nothing but the value of the slope at a particular point. But it is a ratio of two infinitesimally small numbers. And he had difficulty, mathematicians also have difficulties in their lives, that he had this difficulty because analysis had to yet flourish. We sort of bit the bullet and we just made progress and we solved some real life problems. And that's why the theoretical treatment sort of got delayed. But for now, let's just go with what Leibniz did, that dy by dx is nothing but the ratio of two very, very, very small numbers. Okay. So now, so D is basically difference, right? So this is what D stands for. Now, so Leibniz coined the term differential for infinitely or infinitesimally small amounts like dx and dy. So differential is dx. D is the difference. Differential is dx. Differential is dy, or both dx and dy are differentials, right? So now you can see, right, and this particular graph that we have here is y equal to x squared, right? So you can see that when the point A is x and then the other point is x plus dx, the correspondingly it is dy. And so you can easily see that the difference dy is x plus dx the whole squared minus x squared, right? Pretty straightforward stuff, right? I don't think this is difficult to understand, but we are again looking at it from a historical standpoint. So we should just spend some time on that. So now we kind of comfortable with this, like dx is equal to this change, dy is equal to x plus dx squared, the whole squared minus x squared, right? And so what will happen? Dy is equal to nothing but I'm adding and subtracting y from it, y plus dy minus y. So it is equal to 2x times dx plus dx the whole squared, right? Pretty straightforward. And the slope of tangent is is really as the dx tends to 0, but doesn't become 0, but it tends to 0. And at that time, dx, you can see the point is he was sure that he's doing some kind of a con job here because you're dividing by dx and you're getting rid of one dx, right? So because so dy comes out to be 2x dx plus dx squared. So dy by dx is 2x plus dx, right? And why are you able to cancel dx? Because dx is not 0. And now what he's saying is something like this, like dx is so small as compared to x that you can always ignore it. So this is where this limiting condition comes into picture. And once you say that dx is not 0, and the next time you ignore it. So there is always this shadow of doubt in your mind, and it will remain until we study this material in its true light, that is analysis. So we will defer that again. And so we know that the derivative or the differential, the ratio of differentials dy by dx comes out to be 2x. Now Leibniz did not stop there. I mean, this is a very, very interesting figure here. Just imagine, see, once we come to know about certain entities, certain things, because human beings are curious, they tend to tinker with them. This is what our nature is. We are naturally curious beings. When we came to know about numbers in the antiquity, we started adding them, subtracting them, multiplying them. I mean, I don't know who was the first person who tried to multiply two numbers. They are lost to history, but we're sure that somebody tried to do this. Leibniz did the same thing with functions, right? So see what happens here, right? So if you look at the red function or the red curve, then at every point, the ordinate, the value of y for the red function is equal to the value of blue function times the value of green function at the same point. Now, if this is the case, then how does its derivative look? This is really playing. This is really tinkering with things. See, we have y equal to, we just saw, right? Y equal to x squared, dy by dx is equal to 2x, right? It comes as a function, right? Y equal to x squared, y equal to 2x, both of them are functions. Now let's say that I have got a function which is a multiplication of two other functions. Now what happens to dy by dx? Right? I mean, it's a legitimate thing to do, right? You could add two numbers, you could multiply two numbers. Why can't you multiply two functions? You can, right? Of course you can. And if you multiply those two functions, what do their derivative functions look like? Unless you are able to do this kind of playful explorations, progress is just not going to happen. And that's exactly what people like Leibniz did, right? So it's very, at some point in time, it becomes very straightforward, right? Because y is equal to u times v or uv, right? There is a function u, like in this case, let's say that the red function is, I don't know, like 3x cubed or 6x cubed. The green function is 2x squared and the blue function is 3x. So, you can multiply those two and you get these. So clearly dy is equal to what? Dy is the differential, right? So u plus dv times v plus dv minus y, which is uv, right? And then you get dy equal to u dv plus v du, and uv cancels out, and then so dy by dx comes out to be u times dv by dx plus v times du by dx. Look at that. I mean, that's just, so what I've drawn here in the dotted lines are basically the individual derivative. Like green derivative is the green dotted line. The blue dotted line is the derivative of the blue function, and the red dotted line is the, again, I shouldn't have drawn this on the other side, but you can imagine that these are, and also these are not the real functions because those functions are above x-axis, right? I have just drawn the reflections in x-axis so that the things become clearer, right? Now, the point is that if red curve is the function, is the product of green and blue functions, what does its derivative look like? Is it just the multiplication of the derivatives of the blue and green lines, green curves? No, because we clearly see that it is u times the derivative of v plus v times the derivative of u. I mean, there is nothing rocket science here, right? It's pretty straightforward. Leibniz was able to do this. See, the notation that he came up with about 350 years ago is in use today. Because this makes sense and there's no real need to change it. And so he just continued doing this. He multiplied, he divided, he used exponentiation, all kinds of things he did. It tinkered with these things, and that is how we made some progress. And now, like we were saying, or we have been saying, let me just define this. Like, because of this notation, what happened was at this time, at this point in time in English language, two verbs got added, right? And these two verbs are to integrate. What is to integrate? Just to take the area under the curve, right? That is what integration is. But the key thing is to realize that to integrate is to take the area, but to realize that it is also a changing quantity. It is also a function. For a given curve, the area under it also is a function which has its own variation. And again, we came to know that to differentiate is to find the function which represents the rate of change of the given function. Right? So these things got cemented in our vocabulary. We just, it's like adding two numbers, multiplying, commutativity, associativity. These things were there in arithmetic for thousands of years, right? But around this time is when integration and differentiation, or to integrate and to differentiate, became the part of our vocabulary, right? So now we needed some symbols again for various things that we are defining here. So what Leibniz did was he just used this particular symbol, which came to be known as the integral symbol, to represent the area under the curve. He just said that this represents the entire function for a given function. So when I say integral of f of x, I draw f of x, then I imagine how the area under the curve is changing and denote that as the integral of f of x. Now it's pretty clear, right? So if you are, let's say that you are looking at a particular point on the curve, like what we had before, x and y, then its x coordinate is nothing but the summation of really small dx's. So it's pretty clear that x is equal to the integration of d of x, or dx, right? It is basically the summation of all the little dx's that start from some point, fixed point like origin, and go to every point of interest. The only thing to remember here is that dx is so small that it is incomparable. It's incomparably small to every little x that you can think of. Now, this is again spooky, right? I mean, it's not really very clear. What if my x is small? Then what happens to dx? Well, dx is still very small. So that was the kind of unsatisfactory answer, but then limits provided some kind of a solace here. So we did deal with this in a slightly different context, but it is applicable here as well. Same thing with y, right? Y is the y coordinate is nothing but the summation of the infinitesimally small differences in y, right? So now what will be the area under the standard parabolas? Like if you look here is the standard parabola, slightly differently here, but what will it be? So, it's pretty clear that a is equal to integral of y dx. See here, this is y and this is dx, and integral of that y dx is nothing but the area under this particular curve. If this curve is x squared, then every y is x squared and you take the integral of that, right? Pretty straightforward stuff. But now we are taking the baby steps in terms of the notation. See, what happens in standard textbooks is that this historical evidence is not at all there. So you kind of take it for granted, whereas it's okay to take it for granted. When you look at it from a historical standpoint, it perhaps makes a better connection. And that's why we are going into this here. And so again, dA is that small change in the area, right? Again, what is A? A is integral of y dx. So what is dA? D times integral of y dx, right? Pretty straightforward. There's no confusion here, I believe, right?
Well,
A is it? Yeah.
yeah, not really d times the
Yeah, not D
integral.
times. D integral of y dx. I'm just like
Like
replacing. So you're right.
a small change.
Yeah, see, D is not a number. dy
Yeah,
and dx's are numbers, but D is not a number. It just denotes the difference.
yeah, just doesn't denote a small difference,
Right.
a small change.
Yeah, a small change. And D, I think the mnemonic for difference. All right, so now we have got FTC restated. Like I said, like if we forget everything else, and there are, let's say, 1.5 things that I want you to remember, then one of them is definitely FTC, the fundamental theorem. And the second thing is really calculus is this interplay between the discrete and the continuous. I really want you to know this. When something becomes continuous, at that time some change happens. When things are discrete, like 1, 2, 3, 4, defined, very well defined for numbers or integers of our acquaintance, things are perhaps easy or at least comprehensible. But when we get into the continuous realm, some interesting things happen. So that's the half thing that I want you to remember, and this is the full thing that I want to remember. So again, when you look at FTC, you just cannot forget this particular diagram. It's just like, you see it as many times as you want, but this is really what it is. There is a curve Z, then there is a curve Y. You take the derivative, or you take the slope of tangent at every point to Z and plot it as a function, you get the curve Y. Again, this is the reflection of the rate of change, but Y represents the rate at which Z is changing. Very, very straightforward. So Y is the derivative of Z, right? And alternatively, we saw that Z is the quadrature of the rate of change. So area under the curve of Y is represented by our original curve Z. So there is a song and dance between Z and Y. That's what FTC is all about. So what is Y? So I'm now going to translate that into the new notation that we just learned. So Y is definitely equal to dz by dx or dz by dx. Everyone comfortable with that? No problem, right? The curve y, which is the reflection of the real y, is equal to dz by dx, right? No problem. Now what is z?
Yeah, no problem.
Yeah, z is equal to integral of y dx. Why? Because z represents the area under the curve of y, right? Y dx, you take y times dx, that is the small area, like this area, A, D, F, C. That area is y dx. And when we integrate this y dx, right, you take that area from this origin all the way up to F, that area is represented by the magnitude of z at the same point. This is just amazing. We can talk about this as long as you want. That the area OAC, right? OAC, the magnitude of that area is same as AB. How beautiful is that? It's
The
really, really
value of z at that point.
correct. The value of z, or the value of the height of the function at A. The height of the function is x cubed, right? And that's it. That's just beautiful. So I'm not, doing any sleight of hand here, right? Z is equal to, or Z is equal to integral of y dx, right? And so here it is. This is really beautiful. Now what is y? Y is d by dx of z, and I'm just replacing z as integral y dx. So this is d by dx of integral y dx. That's what y is. And how does the last sentence translate? The height of a curve is the rate of change of its quadrature. See, d by dx is the rate of change. Integral of y dx is the quadrature, right? You're now looking at the curve y, and you're looking at the quadrature of it, which is integral of y dx, and you're looking at the rate of change of that quadrature. You have to get y, right? So y, which is the height of the curve, is equal to the rate at which the quadrature is changing. This is FTC restated. And once you become comfortable with this, you really have gotten the heart of calculus, at least the elementary calculus. We have a
Um,
C.
Sorry, I just wanted to say that maybe this y equal to d. This last statement is easier to visualize in a fraction form, or like um, where you have d by dx outside the integral.
Right, right. I think so, again, like I
I
said,
can show that. I can show that if you want. There
yeah,
might
yeah.
be. I'll
So
show
you
you.
can, right. So again, d by dx is basically something that we have come to know as the rate of change. And now the function here is integral of y dx,
Yeah.
right? It is the quadrature of the given curve. The rate at which it is changing is the height of the curve. It's really very, very interesting. All right,
Yes.
cool. So again, our same, I'm just going to end it with this slide and then hand it over to Apurva, who would help us get into some of the nitty-gritty details, like always. But here, I really want you to, appreciate the inverse problems. What FTC gives us is the way to think about an inverse, in something in an inverse manner, right? You have a curve y and you want to find the curve z, which represents the area under y. But instead of asking that straightforward question, you said, okay, I'm trying to find out that curve whose rate of change is the function that I'm given. In all of mathematics, this inverse thinking is a leitmotif. What that means is it's a recurring theme. All the time it comes. Multiplication, division, integration, differentiation. Another example that you can give me, I'm pretty sure, is any other example where inverse thinking is important?
Log and anti-log.
Log and anti-log, or exponentiation and logarithms. I mean, it's all pervasive, it's everywhere. You just, in arithmetic, you have addition, subtraction, multiplication, division. So, when we started division, we really said, okay, I want to divide A by B and get an answer C. Well, instead of doing that, find the number which when multiplied by B gives me my number A, right? So there are some undeniable advantages of thinking like this. In your mathematical journey, I would highly encourage you to focus on these inverse problems. If we have time in the next lecture, Apurva is going to talk about something called as inverse functions. It's a beautiful concept. I mean, I can't praise it enough. Inverse things are really, really, for some reason they become just beautiful. So same thing here, just just look at this particular diagram again. This is like if we are given a function z, okay, we are given the function z equal to x cubed, and we are asked to find the rate of its rate of change function y, and that is its derivative. We simply find it using the limit laws, right? It can be anything, right? Y z equal to x cubed. We know again the same thing, right? When we have a hammer, everything looks like a nail. So we know that it is the limit as dx tends to 0, x plus dx the whole cubed minus x cubed divided by dx, and then we say that, oh, dx is very, very small, and then it comes out to be 3x squared, right? Very straightforward. It's a hammer that we have got. So we apply it everywhere, right? The problem is that if we are now given the curve y, okay, we are given the curve y, like the blue curve, y equal to 3x squared. And we are asked to find out the function that represents the area under the curve. First of all, is there a function? Is there a function? Who tells you that there is a function that represents the changing quantity quadrature or the area under the curve? What if it is some random thing? It's not given that it will be a function. But it was the inverse thinking that helped us here. Because we were able to prove, first of all, state and then prove the fundamental theorem of arithmetic, calculus, sorry. We came to know that there is another function that represents the quadrature of this particular function. The problem is that directly finding the area under the curve as a function. See, this is, I don't know, I'm not able to explain it. My excitement is like you have a function and you want to find another function. So you have now become a function detective. You want to find another function that represents the rate of the quadrature of this particular function. It turns out that this direct way of doing things is hard. It's not easy for all kinds of functions. Because we want to do this for all kinds of functions, periodic functions, logarithmic functions, trigonometric periodic functions, exponentiation, algebraic functions, all kinds of functions. We want to have the same procedure, answer all the questions. You can't say that, oh, this particular new technique called calculus, oh, it only, by the way, works only for algebraic functions. Nobody will use that, right? So we need to have this way of generality. Mathematics is all about generality, right? We want to be able to answer the general questions. Now the general, see, again, given a function y, we want to find a function z, which represents, first of all, are we sure that there is a function that represents the changing quantity area? We can see that the area under the curve is changing constantly, right? As the curve changes, area under the curve changes. But does it mean that it is a function? No, it's not directly applicable. because we proved this fundamental theorem, we can now say that it's a function. And now, excuse me, the function can be found by thinking otherwise. Like, okay, we are trying to find out that function whose rate of change is the given function. Excuse me. So that's what it is. So, finding the area under the curve directly is hard. You try it. It's not very easy. How will you do the sums? How will you sum the x squared? How will you do the sigma of x squared? It just is not easy. So we
Basically
have
the
to take the
limit
help
of the
of,
sum.
yeah, the
It's not
infinite limit.
easy, yeah. It's not easy. So
Yeah, so the limit of the infinite sum is not that easy. And that is why this inverse function, inverse thinking, my general suggestion to you is that have a habit of thinking in an inverse manner. I'll give you another very small example and then I will end it. And that is that let's say I give you two large numbers and I ask you to multiply them. I think that's an easy problem, right? I mean, you can easily do it. We have computers nowadays. We can multiply 100-digit numbers, no problem. But let's say that I give you a 100-digit number and ask you, is this number a prime number or a product of two other integers? So it's basically the factorization problem. Now that problem is not easy. And it is good that that problem is still not easy. With the quantum computers, it's going to be a problem because quantum computers can solve this problem very quickly.
yeah.
So the problem is that, I mean, I wanted you to look at things in an inverse side. Okay, what if I did the opposite thing? Ask that question to yourself. You try to solve this problem. Like, for example, you have a function u, you have a function v, and you want to find out the area under the curve, which is represented by u times v. Now, integral of uv is not that easy. You have to take help of some other tricks because we're just not, if you solve this problem directly, great. But it is just not that easy. And that's why we take help of the inverse thinking. All right, cool. So that's all I had for today. And I think I'm a little bit late. So Apurva, it's 9:21. We started at 8:40, so we'll go till 9:40. Okay, please go ahead.
Okay, but I just have one thing to show. Let me just
Yeah, sure.
share my
Go ahead.
screen. Okay, so the biggest thing is we saw these new things called d by dx and this little weird symbol. It's we call that the integral symbol. But the biggest thing to remember is that differentiation and integration are operations. So just like addition is an operation, and we use the symbol plus. We use this symbol for addition, right? Or we use a small little number on top. We use this for exponentiation, which is also an operation. Just like that, differentiation and integration are also operations. So but instead of a plus this time we have we have a symbol that we use to denote a differentiation, and that's this d by dx. Now you'll see this in many places. This basically means when you put an f of x after it, this is the operand, right? All operations require an operand. So this is our operand, our f of x, right, which is our function. It's this differentiation operation. It um, it requires a function operand. So so if our function is f of x here, we put this d by dx because obviously we're differentiating with respect to x. Basically, that means x is the independent variable in our graph. But the point is, differentiation is an operation, and this is the symbol we use to denote differentiation. So suppose we were saying we were trying to find the derivative of say uh, yeah, so sometimes we say we sometimes write a function as f of x equal to x cubed, right? Or sometimes we even write it as y equal to x cubed. So you can either say it as, you can write it as d by dx of f of x, right? D by dx is our operator. Remember, it's it's the symbol we use for the operation of differentiation. So you can either write it like that, or you can write it as dy by dx. So that's just another way to write it.
Yeah, I mean, you can either remember it as a ratio of two differentials, right? dy is the differential in y, and dx is the differential in x. Either you can think of it as that, or you can think of it as an operator operand pair where y is the operand and d by dx is the operator.
Exactly. So, but whenever you see something like d by dx of f of x, that just means you're differentiating f of x with respect to x, right? Since x is, it's d by dx, you're differentiating f of x with respect to x. So again, it's just, you can think of it like an operation when you see that d by dx there. It just means you're differentiating the function that comes after it. Similarly, this is the symbol we use for integration. Sorry, I drew that a little weird. So this is our integration symbol, right? After this, obviously there may or may not be some numbers here and here. There may or may not. There doesn't have to be. But there's always a function after it, right? So, and there's a little dx, obviously, because the little, we take little squares or little widths along the x-axis, which are dx. But the biggest point is that this is our function, right? And we're integrating with respect to x, which is why we put our dx here. And basically this, we're saying that, oh, the function that comes after this, we're integrating that. So that's just the point. Like all operations have symbol. Addition, 5 plus 7, we have our symbol right here. This denotes addition. Just like that, this denotes integration. D by dx denotes differentiation. So differentiation and integration do operate on functions instead of numbers, unlike the operations we've seen so far, but they are still operations and they do have a symbol. So that's okay. That's what I wanted to say.
Cool.
And I will share my slides. 1 second. Okay, can you guys see my screen?
Yeah.
Okay. Okay, good. Now, last time we saw how to find a derivative, right? But let's explore another way to find a derivative. Now, this way is probably the way that came to your head first. I went about it a little geometrical way, but this is probably the way that's, more straightforward. So suppose we have this function, and this is y is equal to 1 by x, and we want to find its derivative. Okay, we want to find the value of the slope of the tangent line, right? What is the slope of the tangent line at each and every x value? And that'll give us its derivative, right? It's again another function. Since we want to find the slope of this tangent line, right, we calculate our rise over run, right? And so we have a little, so at some, we take some x value, and then there's a little, a small change, which I have written as delta x here, right? And then we take the secant line, right? It is a secant line right now, but we want to find the slope of the tangent line at x, which means we take the slope of the secant line as x plus delta x approaches x, or really as delta x tends to 0. And we need to calculate rise over 1, so we set up a limit. And the way to do that is we take, I mean, it's just the rise, right, which is f of x plus delta x minus f of x, right, the original value, and divided by the run, which is x plus delta x minus x, the difference in the x values. So difference in the y values divided by the difference in the x values, and we take the limit of that as the difference, right, delta x. Difference between the x values tends to 0. Okay, now we have to simplify this right now. To be able to cancel some delta x terms, right, we need to simplify it, because right now if we just plug delta, well, obviously we can't plug it in, but if we take the limit right now as delta x tends to 0, okay, we reduce delta x further and further and further, right, closer and closer to 0, this will approach 0 divided by 0. So we can't really do that. So we can't figure anything out from 0 divided by 0. So we don't take the limit yet, right? We do some algebraic manipulation. Now, the first thing, right, is to just replace f of x with our function, 1 by x. So that'll give us 1 by x plus delta x minus 1 by x, and the whole thing divided by delta x, since x plus delta x minus x cancels out. And again, this is this is just some algebraic manipulation. It should be pretty easy. Just, you know, it's something that you have to do to find derivatives all the time. So, and it's just something, I mean, you're gonna need algebraic manipulation a lot in calculus. This is just some practice, basically. But there's nothing really conceptually difficult in this. Just you know, our standard manipulation. So we multiply. We find a common denominator on the top, x, and so then we get x minus, right, x plus delta x. Again, right? We just you know, common denominator, subtract x plus delta x from x. We get minus delta x, negative delta x, right, divided by x into x plus delta x, divided by delta x. Delta x is still by itself on the bottom, so we need to simplify it even further. We need to simplify it to the point that we can cancel some delta x terms. So we do just that. That delta x on the top and the bottom can be canceled, and we get minus 1 by x into x plus delta x. Now, notice how we still haven't taken the limit. It's still not easy. So we still can't take the limit yet, because it's on in the denominator. We still have x into x plus delta x. So we again simplify that, right? Simplify. You get x squared plus x delta x, and now you take the limit, right? As delta x tends to 0, x delta x will also tend to 0. So this whole value, minus 1 by x squared plus x delta x, right? As delta x tends to 0, this will tend to minus 1 by x squared, since x delta x is 0. So we'll get minus 1 by x squared. So what does this mean? We've just done some algebraic manipulation and gotten some value. Well, what this means is that we have this function right here, f of x equal to 1 by x. And we've figured out that the derivative of this function, right, is the function minus 1 by x squared. So the derivative of this function is this function. And it looks pretty intuitive. I mean, you can see around on either side of the y-axis, it's the slope seems to be reducing and reducing at higher and higher magnitude. And so, well, I mean, it seems to be reducing on either side, so it's going to be negative on either side. And as you get closer to the as you approach the y-axis from the left side, it gets more and more negative. And as you as you increase past the y-axis, so past zero, as you keep increasing past zero, it seems to be getting less and less negative, which is shown by this f of x equal to -1 by x squared graph. So this is very interesting that the derivative of the function f of x equal to 1 by x is f of x equal to -1 by x squared. And this is well, we've just done this using limits, right? There's no geometry here, as I've shown last time, and this might be an easier way after learning limits. But it's just another way. And the biggest thing is that you need to know when to take the limit. You can't really take the limit until you get to the first step on the right-hand side, because, I mean, otherwise you get 0 by 0, and we don't know what to do with that yet. So basically what we've shown is derivative of 1 by x is -1 by x squared. Okay, but now that's not the only thing, right? You can do so much more stuff. So a similar thing can be done for f of x equal to sine x. We did it for 1 by x. Now we can do it for sine x too. So as you may see, you will have to compute some. I mean, if you decide to do this one, you might see that like there are some limits that you have to compute before you'll actually solve this. And this is a hint, specifically these limits. But so limit as delta x tends to 0 of sine delta x by delta x. And the second one, limit as delta x tends to 0 cos delta x -1 divided by delta x. So these limits you're going to have to figure out if you want to find the derivative of sine x this way. You can do it the geometric way too, but this might require some time to explain, but it's not very difficult to do if you understand limits and derivatives. Since we're short on time, finding the derivative of sine x, I'm going to leave it to you guys as an exercise if you guys are interested in calculus. It's a really good exercise, and if you want to find the derivative of sine x. So it's but the point is, with our knowledge of limits, right, we can find the derivative of any function. So but we are a little short on time, so I'm not gonna go over limit of sine x. So let's go on to the next thing. Okay, so we found the derivative of f of x equal to x squared, and we found it as y equal to 2x, right? And the derivative of
so this is another little notation. I'm sorry, Apurva, but f prime x or f dash x
Yeah,
is something that
I talked about that last time, I believe. The little prime means just the derivative function. So if f of x is the function, f prime of x is the derivative function, derivative of f of x.
right. So f prime x is same as f prime of x is same as d by dx of f of x.
Yeah, exactly. So we found the derivative of f of x equal to x squared to be f of x equal to 2x, and the derivative of f of x equal to x cubed to be f of x equal to 3x squared. So do you guys see a pattern? So it's a nice little pattern, but we can try to make it concrete, right, by finding the derivative of x to the power n for any natural number n. Right? So we try to find the derivative of this function, right? Now n can be any natural number. Okay, but we're still going to try to find the derivative, okay, of x to the power n. Obviously, it won't be the same. I mean, as we can see with x squared and x cubed, it will depend on n. But can we find a pattern? X squared, x cubed, x fourth, x to the fourth power, x to the fifth, etc. So that's what we're going to do. First thing we do, we set up our limit, just like always. So x plus delta x, the whole to the power n, minus x to the power n, divided by delta x. That's our that's from our rise over run slope, our equation for rise over run. We've gotten we've plugged x to the power n as f of x, and we've gotten this limit. Now, we still can't take the limit right now, right? We'll get 0 by 0 again. So we do some algebraic manipulation. Now, the first thing to do is we have to expand x plus delta x, the whole to the power n. This is not easy, and it requires knowledge of binomial expansion. So, I mean, any a plus b, the whole to the power n, how do you find that? So I'm gonna assume you guys know that, but I'm not sure. You guys, do I need to go over that binomial expansion, or do you guys know it? A plus b, the whole to the power n.
Yeah, I know that.
Oh, okay. Okay, great.
Yeah, I do. I do.
Okay,
Yeah, I think
awesome.
you guys perhaps have seen that in in your first course of combinatorics or something similar. Um, yeah, but I mean, and the story of binomial theorem itself is very, very fascinating. But I think we will defer that.
Yeah. So okay, so we expand this
Yes, yes.
x plus
Shashwat has
delta.
some question, I think.
Oh yeah, sorry. Go ahead.
Um, I don't really know the expansion like really well. I think I've heard of it at one point, but I don't really
Okay.
understand that.
Okay, no problem. I'll just go over it then really quick. So can you guys see my screen?
Yeah.
Okay, okay. So if we have our a plus b, right, to the power n. So we know how to find a plus b squared, right? A plus b the whole squared, right? It is the same as a plus b into a plus b. And then we just use our FOIL, right, to find, so we just a times b times a times b, and then b times b. We add all of that, and we get a squared plus 2ab plus b squared. But it gets a little more tedious when we get to a plus b the whole cubed. It's definitely more tedious. You have to multiply um, you have to multiply each a and b by uh, 4, I believe, but you'll get 4 different terms, right? And but the point is, how will we generalize it for a plus b, right, to the power n? So I will not. I mean, I have not proved this yet, but we usually I'll just go over it here. We just say it's n choose 0, a to the power. Do you guys know sigma, Joshua? You know sigma notation?
Is that like addition?
Yeah, it's the summation.
Yeah.
Okay,
Yeah.
okay. Okay, great. So really it's just I'm just gonna write it in sigma notation, and if you guys don't understand it, I'll explain in more depth. So from I equal to 0 to n. Now this is this, okay? A plus b, the whole to the power n is this. It's a whole thing. N choose I, okay? N choose I, okay? Into a to the power I b to the power n minus I. Can you guys see that well, or do you get that? A to the power I, b to the power, a to the power I into b to the power n minus I. And the sum of that from I goes from 0 to n. So it is a pretty big expansion, and you guys should check that out. But I will do. Is it somewhat clear now, or does it ring a bell? Maybe.
Yeah, thank you.
Okay, no problem. Yeah, no worries. So it's just a huge sum, but or it can be huge depending on n. But that's our job here. So let me go back to my slides. You guys can see that, right? The slide. You can see the slide? Yeah?
Yeah.
Okay. Okay, good. So we need to expand x plus delta x the whole to the power n. So I can use sigma notation here, but I have not used sigma notation. I have used an ellipses notation, but we can think of x as a and delta x as b and expand it just how we would do a plus b the whole to the power n. So we get this, right? Now I'm not going to read all this, but this is just the expansion of x plus delta x the whole to the power n. Now this dot 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 means there could be a bunch of terms between this. Omitted because I have no idea how much terms there are really. But we know that the power of delta x goes delta x squared, delta x cubed, dot dot dot, then delta x to the power n minus 1, and eventually delta x to the power n, right? So the first thing we can see from this is that, oh, x to the power n minus x to the power n, they cancel out, right? This is, again, we just go straight into algebraic manipulation, and we can see that minus x to the power n, x to the power n cancel out, okay? And each of the rest of the terms has a delta x in it, okay? So each of the terms has a delta x. And so we can cancel that with the denominator, right? We can take a delta x out of every single term of that. So we remove the x to the power n, and we divide by delta x, and we get this. Now, oh, did I mess up a little? Yeah, it's not delta x to the power n minus 1. It is delta x nx delta x to the power n minus 2, I believe. But yeah, n minus 2 and n minus 1. I messed that up a little, but that's fine. I'll fix that. The thing is, we just removed delta x once from each of these terms in this series.
And we can do that like what Leibniz reasoned. He said that delta x tends to 0. It is not 0. It's very, very small. So we can cancel it out.
Exactly. So we cancel it out, okay? But we still haven't taken the limit. All we've done is we've canceled it out. Now there's no denominator. We won't get 0 by 0 now. So now what we can do is we can tend delta x. We can take the limit as delta x tends to 0, right? Now, as delta x tends to 0, each and every term with a delta x in it, right? This enters 2 into the second term right here, and these last two terms, they all have delta x's in it. Now, compared to this first term, which has no delta x in it, as delta x tends to 0, right, it gets closer and closer and closer to 0, very, very, very small, much, much smaller than however small n x to the power n minus 1 this first term is. As it gets much, much smaller than that, right, these terms, the rest of the terms, any term with a delta x will become negligibly small. We can really ignore it. Excuse me. We can ignore it because it's just going to get so small. Delta x tends to 0. So as we take the limit, we just remove every term with the delta x. And we know every single term with the delta x, right? They're all going to tend to 0, right? Every single term with the delta x is going to tend to 0. So we just remove all those terms, right? And this, so by taking the limit, we just remove all those terms. And we are left with nx to the power n minus 1. So, yes, this is a really nice thing. We know that every single term that's not nx to the power n minus 1 is going to have a delta x in it. And so we can remove every single term that is not nx to the power n minus 1. It's really beautiful, yeah. And
Cool. So,
wait, sorry. I wasn't done. I was accidentally muted. My bad.
Yeah.
Sorry. So if we have f of x is equal to x to the power n, we can say that the derivative of f of x is going to be nx to the power n minus 1 for any natural number n. So this works for x squared if n is equal to 2. It works for x cubed, right? And n is equal to 3, right? We can see x, if n is equal to 2, derivative of x squared will be 2x, since 2 minus 1 is 1, right? And for x cubed, derivative of x for n equal to 3, derivative of x cubed will be 3x squared, which is what we found. We found that last time through geometry. So using this, we can say that the derivative for f of x equal to x to the power 5 is equal to 5x is not equal to, is y equal to 5x to the power 4. So this is, I mean, somewhat powerful, but we call this the power rule of differentiation. And we've showed that this will always work with any natural number n. This rule will always work for any natural number n. And we showed that. We showed that through our derivation, really. So this is a nice rule to keep in mind. But suppose now we have a function, which is the sum of two different functions. So f of x is x squared plus 3x, say. So we can also say that this function f of x is the sum of two different functions, g of x equal to x squared and h of x equal to 3x. So how do we find f prime of x? So far, we've only found it for x squared, and we can find the derivative of 3x, right? But how do we find the derivative of x squared plus 3x? And that is done through the sum rule of differentiation. So we can use the sum rule of differentiation to find, suppose f of x equal to g of x plus h of x. Then the sum rule states that f prime of x is equal to g prime of x plus h prime of x. Now, I'll explain what that means, but the point is that we can show this ourselves too, right? Just like we did with the power rule. And I actually encourage you guys to do it. Prove this sum rule of differentiation. And although I won't show it here, you guys should not take anything on faith in mathematics. Everything in mathematics can be proved, right? And it should be. So in addition to solidifying like the concept of whatever statement it is, right? Proving the statement makes you certain of its truth. And it feels like you've discovered it yourself. So I encourage you guys to try to prove this sum rule of differentiation, just like we we proved the power rule. But let me just explain the sum rule first. So I won't go over the proof, but I do encourage you guys to do it. So the biggest thing is the sum rule said for the derivative of a sum of functions is the sum of the derivatives of each of the functions. So in other words, the derivative of g of x plus h of x, right, is the derivative of g of x plus the derivative of h of x. And although it's only shown here with two sum functions, this can be proved, right, to extend to any number of functions. You have 5 functions, you can sum them, you can find the derivative of the sum function by finding the derivative of each of the functions and summing them. It's this, remember, it's the sum of functions, right? So okay, so this is actually much more
Shashwat
beautifully
has a question.
described. Oh, sorry. Yeah, go ahead.
So just to sorry about that. Clarify. You first so if you have like multiple functions and you add them, you find the derivative of each function individually, and then just add all the derivatives together to find the derivative of the total big function.
Yeah. So if you have a big function that can be split into like five smaller functions, and you want to find the derivative of the big function, you can just add the functions together, right? Sum the derivatives of the smaller functions, right? Right. But remember, this is summing functions, not integers. So it's just adding functions together, right? We need to keep that in mind. Sometimes it feels like we're summing integers, but it's not like that. But yeah, that's exactly correct. So if you want to find the derivative of a function, which is addition of multiple different functions, right? You add the derivatives of each of the functions, and that will be the derivative of the big function, just like you said.
Okay, thank you.
Yeah, no worries. Yeah. So this is actually, I love this description of it, right? This is Leibniz notation, d by dx, and I love it. So d by dx of so this first statement, d by dx of f of x equal to d by dx of g of x plus d by dx of h of x. Yeah, that's fine. Look at the second one. This is really nicely shown. So d by dx is the derivative, and I put in parentheses g of x plus h of x, which is our function, right? Our function that is the sum of two functions, g of x and h of x. So the sum of these two functions is equal, or really the derivative, right? The derivative of the sum of two functions is equal to the sum of the derivatives. And this is so nicely shown through this second statement. The derivative of the sum of two functions is the sum of the derivatives of the two functions. So pretty straightforward, but very beautiful in Leibniz notation. It's a really nice way to show this. Actually, I really like the second statement. But there's one more rule, I believe.
Yes, Shashwat.
Oh yeah, sorry.
This is just a comment, but if you look at the second one, it kind of looks like the distributive property in a way.
Aha. Yeah, so it does, doesn't it? Although remember, d by dx is not
Yeah, not
multiplication.
multiplication.
Yeah, it's not multiplication, it's an operation, but yeah, it's sort of like you're distributing um the operator d by dx over g of x and h of x. But remember, the biggest thing is that this only works if g of x and h of x are being added together.
Or
So
subtracted.
or subtracted. You can do the same thing for subtraction. But the thing is, this only, you can't do the same thing with multiplication. Suppose you have d by dx of g of x times h of x. It will not be d by dx of g of x times d by dx of h of x. You cannot distribute it over multiplication like that. Also, although it's not distributing, you can't really, it's not the sum of the derivatives of g of x and h of x.
We saw that briefly in the first few slides, I think.
Yeah,
Today.
exactly. So this is that, yeah, this reiteration, this is called the product rule of differentiation. And this can also be proved using limits. And we saw this before, you know, earlier today. But it can also be proved using limits. But again, I've omitted it for, a lack of time, pretty much. And so it states that the derivative of a product of functions, right, is function A times the derivative of function B plus function B times the derivative of function A. So again, multiplication of functions, it's not multiplication of integers. You need to remember our function multiplication. But just like you can do operations, multiplication, addition on function, or on integers, you can do them on function. So we say that the derivative of f of x, right, f prime of x, if f of x equal to g of x into h of x, then is equal to the derivative of g of x times h of x plus g of x times the derivative of h of x.
Yeah, I think, one thing is that one comment I have is like you're kind of mixing the two notations. So I think it's better to just stick to Leibniz here.
Yeah, so this is
Yeah, like
Leibniz.
that.
So, actually, a lot of people like to think of it as left d right plus right d left, right? So this is easier to see with Leibniz notation. So left d right. Our left is g of x, our right is h of x. So it's left d right? Plus right d left. D left, that just means the derivative of left, and d right just means derivative of right. But I mean,
And
it's,
if you forget this, just derive it using limits.
yeah, just derive. But first, you guys need to derive it using limits just to prove it. How do you know this is true? Just because some guy said so? Some person who thinks they know calculus said so? You guys need to prove it yourselves.
Yes, Shashwat?
Oh, yeah, go ahead.
So what happens if there are three different functions being added together?
So suppose you have three different functions, f of x into g of x into h of x. So is function multiplication associative? Is 2x into is 2x into 3x into 4x the same as 2x into 3x times 4x?
Yeah.
Is it the same as 3x into 4x times 2x? Is it basically, is it associative?
Yeah.
Okay, so what you can do,
I kind of see it now. You
okay,
have
yeah,
to
but
put the first
remember,
two functions together, and then you have to.
Right.
Okay.
Yeah,
yeah,
this can be extended to anything. Yes.
exactly. So
Good point.
it won't look very similar. You'll have to derive it. This can be extended, but it requires more derivation than for the sum rule. The sum rule, we can actually prove that, and it's just adding the functions one after another. Say you 5 of them, you just add them. You can't do the same thing with this one, because in each term there's both g of x and h of x, and one of them has one of them is differentiated and one of them is not in each of the terms. So it's gonna be a little bit of different derivation, and again, it's possible, but it might be good exercise. The first thing is obviously to prove the product rule. So, but just one, I just want to say one way to remember is left d right, right d left, just like that. So, and I've heard it works for some people, and I mean it's a nice way to remember. But I mean, okay, so the thing about the product rule is much bigger than the sum rule, and it might look daunting, but it's quite simple when you understand it, really. And yeah, that's pretty much all I had. These are some nice things to prove. If it's left to the interested calculus student. And
Yeah, I mean, the quotient rule is something that we can think of, right? I mean, it's
the
all
quotient rule requires the chain rule, but the point is the quotient rule can be derived from other rules. In calculus, you only need three rules, right? These three rules, and you can differentiate any huge composition of functions you have, right? There are three rules that correspond to three different uh, operations on function. The first one is sum rule, which corresponds to function addition. The second one is the product rule, which corresponds to the multiplication of the function. And the third one, the arguably most powerful one, which we'll go over next time, is the chain rule. And that corresponds to composition of functions. You can make any single function with addition, multiplication, and function composition. Those are the only three function operations you need. Obviously, you can make subtraction, but subtraction is the same thing as multiplication by -1 and addition, right? By combining these different operations, you can create any single function. But function composition is extremely powerful, and hence the chain rule is extremely powerful. We'll go over that next time, but arguably the most powerful, actually, the chain rule. So but just the product rule and the sum rule are nice little you know it's a nice beginning, and you guys should really try to prove that. It's really fun, actually. I think
cool.
so. That's all I had. Yeah.
Great. I think, again, we are sorry we went over, but I hope that it was worth. Cool. So I think we will go over the remaining things, in this introductory calculus course, or really not a course, it's just a discussion. So I believe that, we have learned, all of us have learned something in the course of last several weeks, really. So cool. Um, Sticking to time is always challenging. We have tried that sometimes, but not consistently. So sorry again. Thanks, everyone. Again, if there are any questions, please don't hesitate. Don't hold back. All questions are welcome. And we will meet one more time, most likely next Sunday, same time.
Or maybe the day before, or we'll see when people are free, because next Sunday is New Year's Day, so I'm not sure how many people will be free. So we'll figure it out then. I think you're on mute. Baba, you're on mute.
Bye.
Bye.
Bye, guys, and Merry Christmas.
Yes.
Bye.